Hey everyone, I hope you all are doing well. Have you ever observed this document? The default initial capacity must be a power of 2. Also, when we specify the initial capacity while creating a hash map, if the given capacity is not a power of 2, it is adjusted to the nearest power of 2. So that we can check here. And we pass the initial capacity. At last, this method calculates the appropriate table size for a given capacity. The goal is to find the next power of 2 that is greater than or equal to the given capacity. Also, when the size of hash map exceeds the threshold, its current capacity is doubled. The new capacity equals to old capacity left shift by 1 bit. So in this way, we can conclude that the capacity of a hash map is always a power of 2. So before we explore the significance of using power of 2 for capacity in a hash map, let's first examine the complexities involved in various arithmetic operations at hardware level. At the hardware level, arithmetic operations such as addition, subtraction, multiplication, division and modulo are carried out using the combination of different type of circuit within the processor and generally related to the time, number of steps or CPU cycles and space amount of hardware resources such as logic gates or transistor required to perform these operations. So considering hardware complexities, addition and subtraction operations can be performed directly on binary numbers in a single pass and takes a single clock cycle. Multiplication is complex than addition and subtraction but still relatively efficient. Division and modulo operation are more complex than addition, subtraction and multiplication. It is an iterative process that typically involves repeated subtraction, comparison, shifting, and takes many clock cycles depending on the operand size and the specific algorithm used. Compared to these arithmetic operations, bit shifting is an even simpler operation. It doesn't require any arithmetic calculation, just the rearrangement of bits, and it can be done in a single clock cycle. The use of power of 2 is deeply integrated into both the hardware architecture and software layers of computing because of the binary nature of the computer system. Powers of 2 help optimize memory management, processor performance, data structure algorithms, and communication protocols, making them a cornerstone of modern computing. Their use is commonly observed in the following areas: inefficient memory management and addressing. Memory sizes is often organized in size that are power of 2. Memory addresses are also power of 2. Alignment. Memory alignment is often done in chunks of power of 2. Data structure and algorithms often sized as power of 2. Processor and cache design. Cache lines are often sized as power of 2 to simplify addressing and optimize access patterns. Paging system is in operating system which handle virtual memory often uses page sizes that are power of 2. In graphics and multimedia applications, in graphics image sizes are frequently power of 2. File system and storage often work with block sizes that are power of 2. For efficient computation and cryptography, many operations like multiplication, division and modulo with power of 2 can be efficiently done using bitwise shifts rather than arithmetic operations which are faster at the hardware level. Power of 2 allow for highly efficient modular arithmetic which is critical in algorithms like hash function and cryptographic protocols. Networking and protocol design. Packet sizes in networking protocols are often sized as power of 2. IP addresses subnetting is based on power of 2. Hardware architecture. Many CPU instruction sets are designed to work with data in sizes that are power of 2, 8-bit, 16-bit, 32-bit, 64-bit. Data buses, address buses and other internal data transfer mechanism in CPU and other hardware devices are typically sized as power of 2 for optimized data flow and access. The beauty of the power of 2 numbers is that they have only one bit set, and when we subtract 1 from them, all bits to the right of that set bit including the set bit itself are flipped. So 32 is a 2 to the power number, so only one bit is set, and when we subtract 1 from it, all bits are flipped. 1 becomes 0 and all 0 bits become 1. Now let's explore the significance of power of 2 in HashMap. So it is very useful for faster index computation to improve the performance of key lookups, insertion and deletion and updations. When the capacity is power of 2, the hash code of a key can be used directly to calculate the index of the bucket where the key should be stored. This is because a mod m equals to a and m minus 1 for any integer a and m if m is a power of 2. This means that bitwise AND operator can be used instead of modulo operator, which is faster on most hardware platform. As we know, HashMap uses the node array to store the key value pair. So internally you can see that whenever we need an index of any element, we simply do n-1 and hash. The hash is the hash of the key and n is the capacity. So capacity -1 and hash to fetch the index of that particular element. The modulo operation can produce a negative result if the hash code is negative, but the bitwise AND operation will always yield a non-negative result. This ensures that the index will always be within a range, eliminating the need to handle negative numbers or calculating their absolute value. Negative numbers in Java are represented using 2's complement. Friends, I have written a small benchmark using Java micro benchmark harness to compare the modulo and bitwise operations. Let's run this and see the performance difference. So this is our benchmark class. We are using this benchmark to see the average time in nanoseconds. I have taken a capacity as 128 and one random hash. And test modulo, this method is used to check the performance of modulus operator, and this method is used to check the performance of bitwise AND. And this is a teardown method in which I am printing how many times these methods are called by the benchmark. And this is our main method in which we have used one fork and 5 iteration. So fork means number of separate JVM to run the benchmark. So in this case, when this main method starts, it will be executed in a JVM, and internally this process starts a new JVM to run this whole benchmark. Warm-up iteration means number of iteration before actual benchmark measuring starts. Warm-up time, duration of each warm-up iteration, means during each iteration how long this benchmark method will be called. So in our case we have taken 2 seconds. It means for 2 seconds these benchmark methods will be called. Measurement iterations, the number of iterations after warm-up, and measurement time same. Each measurement will be called for 2 seconds. Important thing to note is the purpose of warm-up phase is to allow the JVM to warm up. This includes things like just-in-time compilation, hotspot optimization and caching. So let's run this benchmark and see the output. Let's copy this whole output in a separate file. So this is output of our benchmark. So we can see that one JVM process is forked from this process for test bitwise AND. Warm-up iteration took 0.815 nanosecond average. So and this is a real measurement. So we can see test bitwise AND took minimum 0.847 nanoseconds, average 986 nanoseconds and maximum 1.037, and the standard deviation is 0.079. And CI, this CI means confidence interval. This represents the reliability of the benchmark result. The CI shows that there is a 99.9% probability that the true value of the benchmark score lies within this range. It means 99.9% chances are the result should be within this range. In other words, it provides an estimate of where the actual performance likely falls, considering possible variations during the benchmark. And this is for modulo test method. We can see this is a comma phase, and this is the actual measurement phase, this one. So there are min, average and max count for the same. So let's see the final benchmark result. So we can see the score for bitwise AND is 0.986 and for test modulo is 1.778. So we can see that bitwise AND average time is less than modulo operation. So the difference between the modulo and bitwise AND operations may not seem significant at first. However, when a hash map is resized, even this small difference in operations can have a noticeable impact on performance. This is because resizing involves creating a new array of buckets that is double the capacity and rehashing all the elements into new array. The results of the benchmark may vary with each run, but you can clearly observe the difference in average time per operation between the modulo and bitwise AND operation. The next benefit of power of 2 in HashMap is uniform distribution of entries. So the bit mask m-1 derived from the capacity allows more bits from the hash code to influence the index computation. When we perform the bitwise AND operation, the lower bits of the hash codes are retained, which means more bits contribute to determine the index. This helps in distributing elements across the buckets more evenly. Reduce the chances of collision by allowing more bits from the hash code to influence the index computation. The next one is it allows for efficient resizing. When the number of elements in a hash map exceeds the current threshold, the hash map needs to double its capacity to accommodate the more elements. With the power of 2 capacity, we simply perform a left shift on the current capacity, which eliminates the need of multiplying by 2. From our discussion, we can address 2 interview questions. The first one is the given number is a power of 2 or not? As we discussed earlier, for any number n that is a power of 2, its binary representation has exactly one bit, 32. So in this case, we can see only one bit is set, while all other bits are 0 and all other bits are 0. Consequently, n-1, 32 minus 1 will have all lower bits set to 1. So all lower bits are set to 1 and this bit becomes 0, this one. Therefore, if you perform a bitwise AND, it should return 0 if n is a power of 2. The second question is return the nearest power of 2 for a given number. So this is Java 8, 9 and 10 implementation, and this is Java 11 plus implementation. The logic behind both the method is to set the all lower bits to 1 in the given number. Suppose if we have a number 17, so we will get number n capacity minus 1 equals to 16. So if we convert all these 0 bits into 1, so we will get this number. So this is 31. So if we'll add 1 into it, it will become 32. So in this way, both methods are trying to solve this problem. I have mentioned the explanation of both the methods. You can go through this. I will share the link in description. So we can conclude that one of the most significant uses of powers of 2 is their role in the efficient arithmetic operations. When one of the operands is a power of 2, many calculations can be performed using bitwise shift, which are faster at the hardware level. So friends, that's all for today's exploration of the power of 2. There may be other benefits of using powers of 2 as well. If you know of any others, please share them in comments. I hope you enjoyed the video. Thank you for your time and attention. See you soon. Until then, keep learning and take care. And finally, I'll leave you with this thought. Let this inspire you to make a positive impact.